Okay, I wanted to give some background to some of the things that we're looking at. So let me say something about dynamical systems. Now, typically a dynamical system is a system with coordinates that change over time. This is a very general description. It could be a biological system, physical system, other kinds of systems, so social system, and so on. And the coordinates describe the configuration or state of the system. For example, a good example of this, and historically important example, is planetary orbits. So suppose we take the sun here, and we have various planets orbiting around the sun. Now, you may have heard that planets orbit in elliptical orbits. It's called Kepler's law. It's not the greatest ellipse, but that would be one planet. You have another planet out here, and so on. So these planets move around the sun, and the planets have a location at any time. I can have three coordinates in space that describe the location at any time, and x, y, z are functions of time. Now, we saw earlier a dynamical system. I told you about how this corkscrew that you plotted can model the trajectory or path of a charged particle in the magnetic radiation belts. So this would also be an example of a dynamical system. It's a set of coordinates that change over time. And in this case, there are three coordinates. Okay, now this is a very simplified picture of planetary orbits. In fact, planetary orbits don't close upon themselves. And the reason is that the planet is not just influenced by the sun, but it's influenced by other planets, asteroids, and so on. So when the planet goes around, you've been taught that the orbit closes on itself and it comes back to the same place, but it doesn't. So this is ideal. Now, so those are ideal planetary orbit. But the actual is somewhat different. If I take the sun here, and I take a planet moving around it, it doesn't quite close on itself. It moves around, and there's kind of a perturbation, something like this. Every time it comes back, it doesn't come back exactly in the same place. Now, there's a way to describe this, also using dynamical system, but a different type of dynamical system. Suppose I take a point here in the orbit, and let me take a plane perpendicular to the orbits at that point. Okay, and this plane will intersect the orbit in points. Okay. Every time the orbit comes back through, it will intersect this plane in another point, and these points will be scattered around. Okay. So if I draw more a picture just of this plane, it might look something like this. Perhaps the first time it goes through, it passes through the point x1, y1. The second time it goes through, it might pass through x2, y2. Third time, x3, y3. And the points are jumping around in the plane. Now, if you've done the fractal exercise, you've seen that that also relies on functions which jump around in the plane. So here where we're taking the dynamical system, but we're just taking a snapshot, we would call this a discrete dynamical system. Okay. All right. Typically, physical systems or biological systems move continuously, but if we're just looking at discrete times, we can call this a discrete dynamical system. And the way you describe this mathematically is that, in fact, the position of x2, y2 is a function of the position of x1, y1. If I know that the system passes through x1, y1, when it comes back around, that determines where it's going to pass through the second time. So we actually can write it this way. We can say f of x1, y1 is equal to x2, y2. F of x2, y2, so that's a pair there, of x2, y2 is equal to x3, y3. And in general, f of xn, yn is equal to xn plus 1, yn plus 1. Okay. So to find out how the point jumps, we just keep taking f of f of f of f of f, repeating this. Now, hopefully, you can see there's some connection here with some of the fractal concepts and Julia sets that we were are starting to look at now. In fact, a Julia set is just the set of points where these iterates, x1, x2, x3, they don't. It's just the set of points that they end up going to. Or I should say more precisely, if a point is in the Julia set, let's just say something about Julia sets here. Okay, so if x1, y1 is in the Julia set, then all of these points, x1, y1, x2, y2, x3, y3, etc., stick close by. They don't diverge out to infinity. Okay. All right, now what does this mean in terms of our planetary example? In our planetary example, that means that the orbit is relatively stable. It means the orbit keeps going around. It doesn't exactly pass through the same point, but it keeps coming back nearby. Now, if you're not in the Julia set, then that would correspond to an orbit that's not stable. You go through, you keep on going through, and then you get farther and farther away, and your orbit just degenerates into nothing. So I can say that this corresponds to a stable orbit. And so outside the Julia set, that would be unstable. So you can see why Julia sets would be very important in the study of dynamical systems. All right, so I just wanted to give this short introduction to this idea of dynamical system and how that relates to these Julia sets and the mappings that we are using. So you can see actually that two-dimensional mappings of two-dimensional space into itself can be very important even in three-dimensional systems.